Hello, my name is Sean, and today I'll be going over Cipher Machine. First, I'm going to talk about, the layout of the Cipher Machine, then the mechanics of the Cipher Machine. Also, I'll be clearing up any of the Edgework cases when we have to deal with the Boolean expressions and such, and finally ending with the mission settings. So, the layout of the Cipher Machine as follows. There's technically nine screens. This ninth screen over here basically not only displays the current page number, but also will display the two-letter code indicating what cipher it is used on that current page. On top of that, it also acts like a submit button whenever you want to submit your answer. To navigate through the pages, you can press all these arrow keys to go to the previous or next page. And then we also have the other 8 screens over here that are labeled as such. The larger screens on the left are labeled 1, 2, 3, 4, and the smaller screens on the right are labeled A, B, C, and D. And also, finally, we have a keyboard, which allows you to input your answer, and of course, to submit, you press this. We'll get to that later on, though. So, the mechanics of the Cipher Machine. There is an encrypted word displayed on the first page of the first screen. The length of this encrypted word can be between 4 and 8. So it can be 4, 5, 6, 7, or 8. And for instance, this is going to be an 8-letter. So I'm going to copy this down. So AGPAMJYW. And the point of this module is to decrypt this encrypted word into a word, and you're going to submit that into the module. And we need to decrypt it using the ciphers on the next page. So starting with this cipher, we're going to have to identify what cipher we're looking at here. To do that, we're going to find the two-letter code, which is going to be VP, which references Vic phone cipher. Alright, first things first. Catenate the encrypted word and the letters on screen 3, which are these letters right here, in that order. So this is PSA UWYW. Let's see, PSA UWYW. Yep. And we're going to catenate it like so. And then we're going to turn each letter into a series of numbers to get an encrypted number string using the phone number pad below. And if you don't know what number pad does, you would need to basically press the number for each time, at least press this number each time to get to the next cycle of letters. So to get A, you need to press 1 once. To get to G, you need to press 3 once, and so on and so forth. So A turns into 1, G turns into 3, and we'll keep going. Next is P, that turns into 6, A turns into 1, Mike turns into 5, Juliet turns into 4, Yankee turns into 0, Whiskey over here turns into 9, P turns into 6, S turns into 7, A turns into 1, U turns into 8, Whiskey turns into a single 9, Yankee turns into 0, and then Whiskey turns into a 9. And in a case if there was, say, if I had an Oscar, which is very rare but could happen, I'll need to type 5 3 times. So O turns into 3 5s, if that makes any sense. Alright, moving on. For each number of the encrypted number string, we're going to do the following. Subtract the nth number of the encrypted number string by the nth number on screen 2, which is this number screen right over here. So we have 6, 4, 3, 8, 5, 9, 7. 3, 8, 5, 9, 7. Yes. And so we would subtract it like so. So 1 minus 6 becomes negative 5, but we're going to, if the result is, at least the resulting number is below 0, we're going to add 10 to that number. So this becomes 5. This number becomes the nth number of our new encrypted number string, and we're going to keep going. So 3 minus 4 is negative 1, plus 10 is 9. 6 minus 3 is 3. 1 minus 8 is negative 7, plus 10 is 3. 5 minus 5 is 0. 4 minus 9 is going to be, negative 5, plus 10 is 5. 0 minus 7 is negative 3, plus 10 is 3. And then treat the number string on screen 2 as if it wraps around to the left side. So we can basically take this number string and keep repeating it as if it just keeps wrapping around. So 9 minus 6 is 3. 6 minus 4 is 2. 7 minus 3 is 4. 1 minus 8 is negative 7, which turns into 3. 8 minus 5 is 3. 9 minus 9 is 0. 0 minus 7 is negative 3, or negative 7, which turns into 3. And 9 minus 6 is 3. Alright, so now we got our new encrypted number string. What do we do now? Well, next we need to create a key using the keyword on screen 1 and the Boolean expression on screen A, which is seen in FN. How do we do it? Create a key? Well, if we go back to the main Cipher Machine page, to create a key, we're going to follow these instructions. Remove any duplicate letters from the keyword, keeping each letter's first and current. So I'm going to remove an E. Then we're going to take the alphabet. So A, B, C, D, E, F, P, Q, R, S, T, U, V, W, X, Y. And I'm going to copy this, so that way we can use it later on. And we're going to remove all occurrences of the letters shown in the keyword. So S, E, and N. Next up, if the Boolean expression is true, which is talking about this, how do we evaluate a Boolean expression? Well, here the first letter determines the Boolean expression it uses, while the letters, or at least letter or letters after that, you have to convert these into a value using the value table. So N, if we look at N here for a second, which is going to be our value, it's going to reference the 5th serial number character, A1Z26. So it means A is 1, Z is 26. So with kilo is going to be 11. All right, so now we turn that into a number. All we got to do now is look at the Boolean expression it uses, such as X is not part of the Fibonacci sequence. Okay, here's one of the Edgeworks I wanted to clarify. So the Fibonacci sequence starts with 1 and 1. All right, like so. And then each number after is determined by the sum of the previous two numbers. So 1 plus 1 is 2, then 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8, and 5 plus 8 is 13. Now, it is asking if 11 is not part of the Fibonacci sequence, which it is not part of the Fibonacci sequence, which means the whole statement here is true. So then we go back up here. If the Boolean expression is true, place the alphabet at the end of our key. So we need to place this alphabet at the end of our keyword, doing something like this. All right, back to here now. We're going to create a straggling checkerboard by creating a table with 3 rows and 10 columns. So we have the columns are labeled 0 to 9, like so. We're also going to fill in our key within this. However, we're going to cross out all the first row cells and the columns whose labels are present within the 4-digit number on screen B, which is the 1435. So we can't have anything for 1, can't have anything for 3 or 4 or 5, which basically does something like this. The last 2 rows is basically filled in. The other thing about this is at least the first row doesn't have anything labeled, but the second row is labeled with the first 2 digits of the numbers shown on screen B. So this turns into 14, like so. And the next one is labeled with 3 and 5. Or we can keep all these together. Doesn't really matter. Make sure this is in the right spot here. Yep. And then we're going to convert the new encrypted number that we've basically done into letters using this key. And what this is doing in particular, you check the first number and see if this number has been labeled as a row, which it is. It's for this row in particular. And then you're going to use the second number with it as the column. So 59 turns into Zulu. Same thing here. 3 is labeled as a row, so we have to find 3, the next one, which is the 3 as the column, that turns into Tango. Then we have to find 0. Now, the thing about this is that if this is not present within these labeled rows whatsoever, such as like we don't have, this number is not present within screen B as well, which it isn't, then simply we're going to check out the first row and use 0 as the column, which 0 turns into an S. Then we have 5 as the row and 3 as the column, that turns into Tango. Then we have 3 as the row and 2 as the column, that turns into Romeo. 4 as the row, 3 as the column turns into hotel, 3 as the row, 0 as the column turns into P, and then finally another 3 turns into tango. And we got our new encrypted word. Now, if you're unsure at this point if you are correct within this, there's a little thing that you can do to make sure that you are doing this correct via a checksum. So you notice that one of the letters on the keyboard has been colored in yellow, such as the papa here. And what we can do is we can perform a checksum on this to check if it does equal P in the sense. So here we go. Let me grab a calculator. And the checksum goes something like this, where we take the alphabetic position of the first letter and multiply by 1. Then the alphabetic position of the second letter times 2. And keeps going on and on and on until the nth letter is multiplied by n. So it works something like this, where 26 times 1 is 26. And tango, which is 20, times 2 is 40, plus 19 times 3, which I can't do math, is 57. And then tango, which is 20, and then we have to times this by 4, makes it 80. Plus Romeo, which is 18, times 5 is 90. And then hotel, which is 8, times 6 is 48. Then we have Papa, which is going to be 16 times 7, which is 112, plus 20 times 8, which is going to be 160 plus something else. It was 20 times, no, it's 20. So 8 times 20 is only going to be 160. And then we can add all these up. And then module this by 23, as you see here. And then plus 1. And you see here, it gives us 16, which does equal the alphabetic position of Papa. So that means we have done this step correctly. All right, moving on to the next cipher, which is TC. And if I remember correctly, this is going to be triangle cipher. Now, some of these ciphers come from the colored ciphers, like Vic Phone Cipher, but this one comes from Shape Cipher by Trax Josh. And this one in particular, at least all the ciphers from Shape Cipher, has been completely revamped. So they're not going to be exactly the same, but they still fit in the whole theme of Shape Cipher altogether. First, we're going to create a key using the keyword on screen 1 and the Boolean expression on screen A. Sweet. So we have pursuing and LMN. So all we gotta do is, let me go back here, remove all duplicates, UING, yep, grab the alphabet right over here, and then remove the PURSING. And then we need to evaluate this Boolean expression using L as the, well, Boolean expression type. So L is this one over here. And M and N refers to the two values. So for M and N, X will be the 4th serial number character, which is going to be Bravo, so that's going to be 2. And the 5th serial number character, A1Z26, is Kilo, which is 11. So we have 2 and 11 as our two values. And L is X and Y are not coprime. And this is another Edgework case in which I want to clarify. So two numbers are coprime if the greatest common divisor or denominator between them is 1. And usually, in cases like this, to calculate GCD, you can take 11, the higher number, module the smaller number, which is 2, and you basically perform the operation, which equals 1. So then you take the rightmost number, which is of the equation, and module by the resulting, which is 1, and this equals 0. And you keep doing this process until it is 0. And the number in the, at least in the last equation, basically the resulting number that happened last, which is this number or this number right here. But I'll say the last number besides this one, the number before that was the result, becomes your GCD. So in fact, because this GCD is equal to 1, that means that the two numbers are definitely co-prime. But which means because they're not, however, they are co-prime, which they're not co-prime, this becomes false. But one last thing I want to kind of cover up, such as if you had 2 and 1 in this case. 1 combined with anything becomes co-prime. It doesn't matter if it's 3, 4, 5, 6, it doesn't matter what number it is. 1 with anything becomes co-prime. Now it becomes a little bit trickier when one of them is a 0, in which I'll cover this up. So 0 paired up with 1 is co-prime because basically the largest, at least the greatest common divisor between the two, is definitely 1, which means it can evenly divide within each other. You can't divide by 0, otherwise you get infinity. But besides that, these two numbers are definitely co-prime with one another. However, 0 with anything, with 2, whether it's 2 or 3 or 4 or 5, this will always result in not co-prime because 0 can be divided by literally anything. 0 can be divided by 5, 6, 7, infinity, and it will still basically have a remainder of, well, 0. And because of that, anything with 0 is not co-prime. And the only case with this is when basically 0 is paired up with 1, in which it is co-prime. But if 0 is basically paired up with 0, it's not co-prime again because 0 can be divided by anything. Hopefully this makes sense in the end run. But right now our Boolean expression is false. So we need to place the this at the very end instead, like so, because it is false. All right. Next, replace the asterisk with an hash in the triangle key below using the number on screen B, with the first number as the row and the second number as the column. So it would be this fourth column, second one. This one would be a hash in a sense, which is going to be 1, 2, 3, 4, 5, 6, 7, the 8th one. So if I count 1, 2, 3, 4, 5, 6, 7, like so, the hash would go right here. And then we can fill up the rest with the, then we can rearrange this key into an actual key, into a triangle, that is. So it's 7 for the first one. 1, 2, 3, 4, 5, 6, 7. Yep. I'm going to space these out a little bit so you can see a little bit better. And then the next one is only going to be 6, which is this. And then I need to space everything out here, which I made one too many of. It's like this. There we go. And the next one is only going to have 4, like so. Because what we're doing is leaving the center empty, like so. The next one is also 4, but in a sense like this. This is 5. I meant 4 like this. As you see here, it becomes the 4th row, column 2, which is where it is, needs to be. So next one's going to be 3. Next one is going to be 2. The last one's going to be 1. And there it is, our actual, well, key. So then we're going to catenate the indicated directions like so. So we have this one, left, left, right, left, right, right. If the submit button is white, reverse all of the indicated directions, such as you would turn all lefts into rights and vice versa, or clockwise into counterclockwise and vice versa. For each letter of the encrypted word, we gotta do the following. Find the nth letter of the encrypted word in the triangle key. So we need to find Z within this key right here. And then we need to go in the indicated direction of the nth indicated direction, which is 120 degrees. So if you think about this like so, it would be this letter right here that's referencing. If this was A right now, this would be Z. So this is basically would be G, and next to it would be Z. So in that case, it turns into Bravo. Next we have Tango. And Tango we have to move clockwise. So with Papa being here, Tango would be right there. So Tango turns into Charlie. And then S is right there. Wow, that's straight up middle. And we need to go counterclockwise from there. So from counterclockwise, this S would turn into a K. Then find a T again, and for this one, we need to go counterclockwise. So if this is the P, this would be the T, so this is going to be N. Next is Romeo right here, and we need to go clockwise. So if this is the P, this would be U, and this would be R, so it turns into D. Then we have an H, and we need to go counterclockwise. That's basically what that is. And for that, counterclockwise, this would basically be right here, which turns into S. Then P is over here. We need to go clockwise, which is going to turn into an A. And then finally, Tango is also going to go clockwise, which is going to turn into a Charlie. And then we can double check this by performing our checksum. So this is going to be 2 plus 3 times 2 is 6, plus Kilo, which is 11, times 3 is 33, plus November, which is 14 times 4. Let me do this. 14 times 4 is going to be 56. Plus Delta 4 times 5 is going to be 20. Plus Sierra, which is going to be 19 times, this is going to be 6, which is 114, plus 1 times 7 is 7, plus 3 times 8 is 24. And then we can do this. Module 23 plus 1 takes us to 10, which is Juliet. So yes, we did everything correct here too as well. So this becomes our new encrypted word. And finally, Geo, which if I remember correctly is Global Offset Cipher. And this one, if I recall correctly, comes from Pandemonium Cipher. So here it is. First, we need to create a key using the keyword on screen 1 and the Boolean expression on screen A, which is fine. So we have issuing in BO. BO. All right, so we have issuing in BO. So first, remove any duplicates. S-I. So ISSUING. Okay, then I need to take this thing right here. We need to do ISUNNG. And I need to evaluate this Boolean expression. So let's go back here. So we have B as our Boolean expression, and we need to figure out what O is. O is the 6th SN character, which is going to be 4. And it's asking if X is odd, which is going to be false because it's even. So that means we have to take the alphabet and place it in front. The other thing about this is make sure to remove any X's. So we gotta remove an X for this. Rearrange the key into a 5x5 matrix. Easy enough. And then if the submit button is white, follow the instructions for under encrypt. Otherwise, we're going to follow decrypt, which is this right here. So determine the path that's needed to get from the center of the matrix to the letter on screen B. So right now it's an R. So from the center and going to here, it is an R. So all we have to do from determine the path that's needed to get from the center to the R, that is going to be 2 rights. Then, for each letter, find the matrix and move in the same fashion as the previous step to get your decrypted word. So for B, moving 2 to the right takes us to D. C, 2 to the right turns us to Echo. Kilo, 2 to the right turns to Foxtrot. November, 2 to the right turns to I. D, 2 to the right is A. S, 2 to the right is N. And A to the right is C. And C to the right twice is E. And we get our final decrypted word of defiance. Now, all we gotta do is just type in this word. And you notice that the last cipher doesn't have any checksum letter because you should have a word by this point. So let's check out our word here. DEFINCE. And then you can either press the submit button here to enter your word, or you can press enter on your live keyboard. Yeah, something I didn't mention is that you can type using this keyboard, like so, or you can type using the keyboard in real life. And you can either press the submit button or press the enter in real life. And that there is Cipher Machine. Alright, I think I covered some of these things here, but I'll go over some of them, go over quite a few of them as well. So time for like clarifications on Edgework altogether. So I think I'll start with this part. So one of the things is AA batteries divided by 2 rounded up. This is just in case if there is like some modded Edgework added into it, is all that really this is. So for each of these values, you should get a value from each one. So when it's using the first serial number character like this, it's using it as base 36, and you need to turn it into base 10. And some of the other ones, such as the 4th and 5th characters, uses A1Z26. Other times, you'll also just only have 3rd serial number character, which means it should be already be a number regardless, and same thing with the 6. And then it also deals with the 1st serial number letter, the 2nd serial number letter, as well as the 1st serial number digit and the 2nd serial number digit. Then you can also have a sum of the serial number digits, so this would be 8. Sum of the serial number letters, which is a little bit more trickier for me, so it's going to be 20 plus Mike is 13. This would be 33. Plus Kilo, which is 11, makes it 44, plus Bravo's 2 is 46. And then some of the serial number characters altogether, base 36, is a little bit, definitely a lot more trickier. Then the next number we also have here are these ones over here, the W, X, Y, and Z, which is the last 4 letters. You notice that it uses the day of week, the day, the month, and the digit root of the year that it is. This is recorded at the time when the bomb started counting down, or up if it's in Zen mode like I am right now. So it's recorded at the time that this bomb starts. Just for an FYI. And I know there's a mod out there that checks the calendar, so you can definitely check of what day it starts and all that. But day of the week, Sunday starts at 0. And if I go over here, so 0 would be here, then 1, 2, 3, 4, 5, 6. The day itself is basically the numeric day, which is today's the 9th. The month is the numeric value of the month. It is June right now, so it would be 6. And this here, most importantly, it takes the year that we have currently, module 1000. So we're only looking at the last 3 digits, which is 022. And we're taking the digit root of that, such as taking the sum of those numbers until, of those digits, to be per se, until we get a single number. So it'd be 022, be basically 4. And that's the digit root of that. Alright, then we have, that's basically it for that. Now for the Boolean expressions. X is even, X is odd. These should be common knowledge. 2 is even, 3 is odd. X is prime, X is co-prime. I think I've already covered this already, but just to be sure. No, I didn't. Prime is when a number is basically when can only be divided evenly by itself and 1. So 2 is prime because it can only be divided by itself or 1 and 1. Same thing with 3, but not 4. 4 is basically can be divisible by 1, 2, and 4. And because 2 is not 1 in itself, it's not prime. 5 is, however, prime, but 6 is not because it can be divided by 1, 2, 3, and 6. The other numbers that aren't prime is 0 and 1. These two are not prime. For some reason, I'm actually not knowledgeable on that, but I know that these two numbers are not prime. Then there's x's composite. Now, when we're talking about composite numbers, it's any number that's not prime. So things like 4, 6, 8, 10, actually 9 and 10, these are composite numbers because they can be divided by other numbers other than 1 in itself. However, 0 and 1 are not composite. So that means 0 and 1 is neither prime nor composite. In cases like that, it's always going to be false if it's one or the other. Next is the Fibonacci sequence, which I think I've already talked about this, but I'll talk about it again, which is going to basically, the sequence starts with 1, 1, and each number afterward is determined by the sum of the previous two numbers. So this would be 2, then 3, then 5, then 8, then 13, then 21, and 44. It basically goes on forever and ever. But I made sure that the number doesn't get too huge, especially when considering the digital root of the year. The only number that gets probably really high up there is the sum of the serial number characters, base 36. But other than that, there's really no, have to remind yourself the whole entire Fibonacci sequence. X's module 4 is 0, 1. So when you take any number, such as, I'll say 15, you keep subtracting it by the module, which is 4, until it's a number between 0 and 3. Becomes 11, and minus 4 becomes 7, and then minus 4 equals 3. And it's checking if all the way between 0 and 3 is that if it's 0, 1, and this one's checking if it's 2 or 3. In this case, this would be true, but this one will be false. X and Y share the same parity, such as they're both even numbers, like so. Or they're both odd numbers. However, opposite parities means one's even and the other one's odd. Very simple and straightforward. Coprime, I've talked about this a little bit, but, to calculate the GCD, you take, let's say you had big numbers, like 8 and 13, and you basically take the module, take the larger number, module the smaller number. Which if I do 89 module 13, it turns into 11. And 13 module 11 equals 2. And then 11 module 2 equals 1. And then 2 module 1 equals 0. There's your GCD would be 1. Because that's what the result is. And so these two numbers would be coprime. It would not be coprime if it's between 88 or something like, height is 52 and 13. If I do 52 and 13, this would result in a 0 because 52 module 13, 52 can be divisible by 13. And so the greatest common denominator or divider or divisor is 13. And because it's not 1, it becomes not coprime. However, 1 with anything is coprime, including with 0, but 0 with anything, including itself, is not coprime. So it looks like this. If either number is 1, it is coprime. If either number is 0, they are not coprime. Otherwise, calculate the GCD between the two numbers. And then from there, you can basically check if it's coprime or not. Connect the GCD, and then it's if GCD equals 1, then return, then it's coprime. Otherwise, yeah. Otherwise not coprime. And I keep doing that. But that's basically what this amounts to. X is greater than or equal to y. That should be standard. X is less than or equal to y. Remember, x is the first value and y is the second value. Now, this last two can be a bit tricky, so I'll go over this one. So when x and y both module 4, so let's take our 89 and 13 right now, and we're going to module both of these by 4. So 89 module 4 is 1, and 13 module 4 is also 1. So module 4 is both 0 or 1, or 2 or 3. So in this case, this would be true because they're both 1s. If the other one, say if I did 88, this would be 0, right? This would still be true because they're both 0 or 1. However, if I raise this one, this becomes 2, in which case this becomes false because they're not both 0 or 1 or 2 or 3. However, in this one is quite the opposite. X and Y, module 4, is 0, 1, X or 2 or 3. In a case like this, one of them has to be 0, and the other one has to be 2. I think I priced the wrong gates there. That's just my fault, in fact. But let me just clear this up. So one of them has to be 0 or 1, and the other one has to be 2 or 3 in this case. So because of that, yeah, that's what this amounts to. So if I raise this one by 1, this becomes 1. And this is still truth because this one is a 1 and this one is 2 or 3. Same reason if I do this, this becomes a 3. But if I raise this one further, such as to 90, making it 2, now this one is 2 and this one is 3, which makes it not true whatsoever because they're both 2 and 3. So, hopefully that clears up with certain things regarding the Edgework part of this. So on to the final part, which is the configurable mission settings. The Cipher Machine itself can be customized to fit any mission settings whatsoever. You can see some examples that I did here when doing the individual ciphers. So the first thing to identify a Cipher Machine is you need to give this code. Basically, the module is searching for this phrase right here, and then everything afterwards is the properties that you're going to give it, such as we have the length property, the order property, the pick property, and the ciphers property. So first is the length property, which is going to be a list of word lengths that you would like to use, such as you can use 4, 5, 6, 7, and 8. So if you want to use all of them, you can basically say, hey, I want to use any random of these. However, if you just want even numbers, you can choose 4, 6, and 8. Or if you want odd values, you can do 5 and 7. Or if you want some of the higher versions, you can do 7 and 8. Or you want some weird counteracts, you can do 4 and 8. By default, such as if not setting this property whatsoever and leaving it blank like that, such as not even showing the property itself, it will choose a random number between 4 and 8. Then we have the order property. This is the type of order you want the ciphers to be in. There are only two types of orders. Orders being basically equal to fixed or random. Fixed will be in the order that you write the ciphers in the ciphers property, which we'll get to next. Random will shuffle the ciphers you write in the ciphers property. By not writing this property, the default type will be random. So if I want it fixed, such as if I want to recreate something like the shape ciphers, right, I can have ciphers equals I'm trying to think of all the things. First it was circle cipher, and I think that's CC? No. CI. So if I do CI, triangle cipher, which is TC, and square cipher, which I think is SQ. Yeah, it is. And there we go. Now with this property, right, and I have to leave a comma afterwards to indicate the end of the property, and something like this, I can recreate shape cipher the way that's intended. However, I can also say it's random, in which it will scramble all these ciphers all together, but if you do nothing with this, then the default will be randomized. It's just there just if you want a fixed order, if you want things in a specific order. Next thing would be the pick. So say if you have a bunch of ciphers, right? You have like Lorenz, ADFGX, RSA, M209 cipher is this one, or even McDonald's cipher. And you don't need commas. Actually, don't put commas there. So what pick allows me to do, right, is to basically, let's say if I want to pick one of these. So I have a random list of ciphers, but I want to pick one of these ciphers to choose from. So by picking one, it picks one of these ciphers. It can pick either Lorenz, an ADFGX, RCA, M209, or a McDonald's. If I do 3, it will pick 3 random ciphers out of this list. So you can have an RSA with an ADFGX with an RSA, or a Lorenz with an RCA with McDonald's, or a Lorenz with M209 with a McDonald's. Is what I was trying to get to. And by random, if it's by pick, if you don't have that one in any default, it'll choose basically the number will be the number of ciphers within this list. However, if you don't have any ciphers from this list, therefore not doing anything like this, such as just having a length equals 6 property whatsoever, by default, it will pick 3 random ciphers by default. Next, finally, is the ciphers. So it's basically a list of ciphers that you would like to use in the Cipher Machine. Find the cipher you want, such as writing the 2-letter code. So these are Lorenz, ADFGX, RSA, the M209 cipher, and the McDonald's cipher. These are the 2-letter codes, references in these tables. And this is the list I want to do here. Other things that you can add is optionally an E and D to the end of it to make the cipher use the encrypt or decrypt rules, such as ADFGX here, which is the AX, if I can find it right here, both have an encrypt or decrypt. If I want to specify if I want encrypt, you see it right here that I placed an E at the end, and 5 other ones that have a D at the end of it. So if I want to encrypt, I place it as such. If I want to decrypt, I place it like that. However, if I don't place anything in there, it will choose randomly between encrypt and decrypt. So, the last thing about this, yes, by now writing this property, it will choose any random cipher from the module. And if you chose pick, such as if you do pick, and you can do like 50 ciphers, it'll randomly pick 50 ciphers out of the cipher list that it has. That is, if you don't supply it with one. And as you see here, each property, as you see here on the game itself, is basically separated by a comma. But not only that, for each cipher machine that I have on the BOM, is that I have one line for each one. So if I press start right now, so this should give me 10 cipher machines, as you see up there at top, but only one cipher is in there because there's only one cipher, and each of them is ADFGX ciphers, with 5 of them being encrypt. Actually, let me just do this. 5 of them being encrypt, and the other 5 of them being decrypt. And not only that, but each length of each encrypt has been basically 4 to 8. So, such as you can practice on a 4 over there, the 5 is over here, 6 is on this side right here, then the 7, and finally the 8 over here. And that's all there is for the Cipher Machine. I hope all of you enjoyed this tutorial. Until next time, guys, keep talking and don't explode.